Hello grade 9 students, this is Mr. Khalil and today we'll be doing a revision worksheet for chapter 18 which is about refraction and lenses. So let's start with number 1. When a light ray passes from water, so that's N1, it's passing from water to diamond, N2 at an angle of 45, so that's the theta incident angle of incidence. Its path is bent towards the normal, parallel to the normal, or bend away from the normal. So the light ray is going from water to diamond. So it's going from low to high index. So since index is increasing, so everything will decrease. So theta will also decrease. So it will bend towards the normal. We can draw it simply. So this is water and this is diamond. Okay, we have, this is the normal, so that's a 45 degrees angle. Here we have more index, so we will have less angle, so it will bend towards the normal. Number 2, when light passes from zircon 1.93 to fluorite at an angle of 60 degrees, its path is, so here we are going from high index to low index. The angle of incidence is 60 degrees, so we know that the angle of refraction here will increase since we are going from low index, from high index to low index, so the angle will be more than 60. But we have to be careful here. We need to see if this angle, the incident angle, is greater than theta critical. In this case there will be no refraction of light, so let's find the critical angle between this. So theta critical is equal to sine inverse N2 over N1, which is sine inverse N2 is 1.434 over 1.923. Make sure your calculator is on degrees. So the critical angle is about 48 degrees. So as you know, if the angle of incidence is greater than, so theta I is greater than theta critical, so we will have no refraction. It is total internal reflection. So this is the case when the angle is greater than the critical angle, and it only happens from high index to low index of refraction. In number 3, a light ray of n equal 1, so is incident, so this is n1 on an air to glass boundary at an angle of 30 degrees, so that's theta incident with the normal. If the index of refraction of a glass, so that's N2. What is the angle of refraction? We simply use Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. Air here is taking as 1 the index. It's slightly more than 1, but it's okay. N2 is 1.65 sine theta 2, so we do sine theta 2, we divide here by 1.65 and here by 1.65, so we get sine theta 2 is equal to about 0.3. To get the answer, we do sine inverse of 0.3. It will be about, so that's theta 2, it's about 17.63 Exactly, so it is 18 degrees. Let's go to the next question. A block of unknown material is submerged in water. Light in water is incident in the block at an angle of 31. So that's theta I. It's incident in water. Theta I equal 31 degrees. So we are in water, so we need N1 is equal to the water 1.33. The angle of refraction is, so that's theta 2 equal 27. What is the index of refraction of the unknown material? This is also a simple and direct question. So N1 sine theta 1, Snell's law equal N2 sine theta 2, 1.33. We are going from water, sine 31 equal N2 is unknown, sine 27. We divide here by sine 27 and here by sine 27. The answer will be about 1. So this is 1.51. It has no unit, the index of refraction. This is also another simple question. The speed of light in ethanol, we need to calculate it. We have the N of ethanol and we have the speed of light in vacuum, which is a constant. We simply use the formula of the index of refraction, N equals C over V. N is 1.36 equal 3 times 10 to the power of 8 over V, which is the speed of light in the medium. So we get it's 2.2 times 10 to the power of 8 meters per second. Number 6 is also a simple question. We have light of wavelength travels in air. So this is lambda 1, wavelength is lambda, and this is N1, and this is diamond N2. What will be the wavelength in diamond? So we use Snell's law, N1 over N2 equal lambda 2 over lambda 1. As you see, they are opposite to each other. N1 is 1.0003 over N2 is diamond 2.42 equal lambda 2 is the unknown, and we have lambda 1 is 640 nanometers. That's another unit for wavelength. So the answer will be 640 times 1.030003 over 2.42. It's 264.5 nanometers. Calculate the critical angle of incidence as light passes from diamond to air. So that's simple. Theta critical equals sine inverse. We just apply the formula N2, which is the smaller, over N1. Remember that this happens only from high to low index. 1.0003 over 2.42. The answer is it's about 24 degrees. This is a simple question. Number 8, now we go to lenses. An object is placed in front of a converging lens. Just remember, this is the shape of the converging lens. It's at a distance greater than 2f. So at a distance greater than 2f, let's erase this, and so this is the lens. It's a converging lens. So here we have f, and here we have 2f. So the object is placed in front here. This is the front, that's the object XO. This is one of the cases. So here we have also f and 2f. So as you remember, we take a parallel ray it bends to F, refract to F, another ray through F, it will go parallel. So as you see, the image here is real, inverted and reduced. The height of the image here is less than the height of the object. This is one of the cases that you have to memorize. A convex lens will make an image appear if the object is placed at 2f. This is a special case. If the object is at 2f, the image will be also at 2f, and it is not enlarged, but it is same size and inverted, and it's also real. Remember this. So if we have, that's a convex mirror or lens, sorry. This is f and this is 2f. This is f and this is 2f. If we put an object here, we will get the image here exactly and the same size as the object. A light ray passing through the optical center of the convex lens will, after crossing the lens, it will continue without refraction. If we have a ray passing here, this is the convex or any lens, concave or convex. If we have a ray passing here through the optical center, it will just continue without any deviation. If an object is placed at the focal point, this is one of the special cases. If we put an object at the focal point here, one ray is parallel and another ray, it goes to the focal point. If we take a ray to the optical axis, it will continue undeviated. As you see, the refracted ray are parallel, they don't intersect. So here we say the image is formed at infinity, since refracted rays, this is also a special case, are parallel. Here we have some calculation problem. An object is held at a distance 12 cm from a convex. So when we say an object, that's xi, it's always positive. We don't have to worry about this. It produces a real image. It's 1/3 the size of the object. This is magnification. So when we are given how much is the image relative to the object, this means it's m. M is equal 1/3, but we will put it negative since it is a real image. And as you know from before, the real image, the magnification is negative. What is the focal length of the lens? So we have to use two formulas here. Of course, 1/f equal 1/xi plus 1/xo. So the magnification, we will use also the magnification formula, which is minus xi over xo. The magnification is minus 1/3. It's equal to minus, sorry, this is xo, this is the object, not the image. We are trying to find the image here, over xo. Xo is given 12, so minus cancels here. So xi is 12, it's 4 centimeters. Okay. So now we do 1/f equal 1/xi, it's 1/4 plus 1/12. We can do it on calculator. I will do it fast here. So the answer will be, it's 3 centimeters. The focal length is 3 centimeters. Here we have a concave lens, as you see. What is the image produced if the object is beyond the focal length. We said in concave we have one case only. Image is always virtual, smaller and up, right? It's only one case. So if we take a parallel ray, it will diverge. Since it is a diverging lens, it will diverge from the focal point that way. If we take a ray parallel to the optical center, it will continue undeviated. Here is the image. We will have always this type of image. It's upright and virtual. Here we have an object is placed at 60 centimeter from the lens. This is a convex lens. We have the focal length. Focal length is f equal 20 centimeters. So we can extend this a little. What is the image distance? What is xi? So I will do first the graphic analysis. So we take a parallel ray. It's not a perfect parallel. It will go to f, and we will take a ray to f. It's almost there. So as you see, xi is real here. We should get a real image, and it is reduced. This is also one of the cases. So to calculate the image distance, we apply the lens formula 1 over f equal 1 over xi plus 1 over xo. So 1 over 20 equal 1 over 1 over xi plus 1 over 60. So here we will get the focal length, or so we will get xi equal positive 30. Positive because it is a real image. We will get a positive xi. What is, if the height of the object, what's the image height? So we will use the formula m equal hi over ho equal negative xi over xo. Here we are given the height of the object. We are given ho. So we will do hi over 5 equal negative. The image is 30 over 60. So the answer will be, it's hi is equal to negative 15 over 6. So it is negative 2.5. Yes, it's negative 2.5 centimeter. As you see, the image here is less than in height the object. It's shorter than the object. Another question. An object is placed for 14 centimeter from a concave lens. If a virtual image appears 10 centimeter from the lens, okay, so we have here, this is xo. It's a concave lens. You have to remember that the focal length would be negative since it is a virtual image. When we see a virtual image, so xi is negative 10. You have to be careful to this, because if you put it plus, you will get a different answer. It's on the same side, so the left side of the lens is the virtual side. So we will use the lens equation 1 over f equal 1 over xi plus 1 over xo. So 1 over 14 is equal to 1 over 14. Sorry, this is unknown. The focal length is unknown. So we will put 1 over f equal 1 over xi is 1 over negative 10 plus 1 over xo is 1 over 14. So the answer would be negative 35 centimeters. Now we have a 3 centimeter tall object, so that's HI. HI is always positive. It's 3 centimeter. It's placed 20 centimeters, so that's XO. We are talking about the object. The image height is HI. It's inverted, so we write HI equal -12 since it's inverted. Okay. The distance between the image and the lens. So we need XI. We use the magnification formula here. Negative magnification is equal to -XI over XO equal HI over HO. So we will use these two together. So -XI, unknown XI, the image distance between the image and the lens, which is XI, over XO, it's 20, equal -HI, -12, over, sorry, it's positive here, it's not in the formula, over HO. HO is 3 centimeters. So the answer here would be XI, negative goes with negative, is 80 centimeters. Positive 80. Since it is a real image, inverted means XI should give you a positive value. The magnification, that's a simple question. Magnification, we can use any of them, HI over HO. So it is HI is -12 over 3, which is -4. So the image is 4 times greater than the object. And as you see, 20 times -4 is -80. Focal length, we use 1 over f equal 1 over xi, which is 1 over 80, plus 1 over xo plus 1 over 20. So the answer will be, so it is positive 16 centimeters. Here we have the height of the image is 3/4 the height of the object, and the object is placed after the focal point. If this object is placed at 25 centimeters from the concave, remember that in a concave, so the focal length should be negative, so the object is always positive. So we have XO here equal 25 centimeters. And we have the magnification, it's also positive because it always gives you a virtual image, it's a 3 over 4. What is the distance between the image and the lens? We have to find XI. So we put magnification is equal to -XI over XO. 3 over 4 is equal to negative unknown XI over 25. So the answer will be negative 18.75 centimeters. Now to find the focal length, we put 1 over f equal 1 over xi plus 1 over xo. This is xi, it's 1 over negative 18.75 plus 1 over 25, put on the calculator, you will get negative 75 centimeters. And as you see, the focal length is negative since it is a concave lens. Its focal length is a virtual value. Thank you for listening.